Okay, so thank you very much for the invitation, and thank you for this lovely workshop. We are learning a lot. So I'm trying to add a piece to this puzzle of Martian dust. I'm Luca Montabone. I have a couple of current academic affiliations with the Space Science Institute in Boulder, Colorado, and it lose affiliation with the LMD in Paris. But my kind of main affiliation is actually my enterprise that is based in France, in southeast France, near Chambéry. It's called Panoreca. That's the logo you see on the top. So this talk actually, I give it a talk, but there are contributions from many colleagues and co-authors who helped me in this endeavor of monitoring the Martian dust storms by using multi-satellite observations. So very at a glance, let's say, let's look at the scales of the phenomena we talk about on Mars. Okay, so Martian weather is what we are interested in on Mars from the atmospheric point of view because it's very dynamic, can be compared to Earth as well, but the scales are different. We have phenomena like dust storms, but also other phenomena, other weather phenomena like waterized clouds, fogs, hazes on the surface. When we look at spatial scales, is mainly from local to regional, but can go up to the planetary scale for certain types of dust storms. This is slightly different from the Earth. In the vertical, the scales are from less than 1 scale height to about 10 scale height. Scale height is about 10, 11 kilometers on Mars. When we talk about temporal scales, then depending on the phenomenon we are looking at, we can go from hourly to sub-hourly, okay? Waterized clouds, for example, they can evolve very fast. Dust storms, they evolve slower. There is a need, hasn't been done yet, but there is a need for continuous and simultaneous and global observations, which basically in practice means going to temporal scales of less than half an hour and spatial scales of less than, let's say, 60, 50 kilometers with a vertical length less than 10 kilometers. Why do we need this kind of continuous simultaneous global observations? Because there are scientific questions still unanswered. We have some hints, but we don't have the final answer yet. Probably we'll never have, who knows? But anyway, the questions are there. For example, how do the dust storms evolve from local to regional to planetary scale? And how do the dynamics of the dust and the cloud varies through the diurnal cycle? Because the diurnal cycle is just now being studied and observed. So there is also a good reason to look at this phenomenon, this weather phenomenon, because hopefully one day there will be humans going to Mars. So monitoring the dynamics of these events is a precursor objective for future operations on the surface, because you would require forecasting of these events, particularly dust storms. Right, putting this in context, what kind of observables do we want to have to look at the weather on Mars? Certainly atmospheric and surface temperatures. We heard from Loic just now. Atmospheric wind components is the big miss for the time being. No real observations in the bulk of the atmosphere has been provided. Surface pressure globally would be a nice observable to have. And aerosols, of course, if we want to follow and monitor dust, we need to have information on aerosols, dust, water ice, CO2 ice, water vapor distributions. Then, of course, these are observables. If we have a global climate model, GCM for short, plus maybe a data simulation scheme, then we are set to monitor this weather phenomena, and one day maybe also to forecast them. Okay. Now, that was an introduction about Martian weather. Dust storms, the dust events in general, are probably the most obvious manifestation of the Martian weather. So we try to distinguish or categorize these dust events in four groups. The very small scale ones, like dust devils, with scales between tens and hundreds of meters. Then local storms with fronts of 100 kilometers. Then we go upscale to regional storms, fronts of 1,000 kilometers, up to the planetary scale. We have seen a few extreme dust events, or global dust storm, as you wish to call them. This is the latest one that we observed. So in these events, as you know, dust is spread all over the planet. I like to call them extreme events because it's not only the fact that dust is spread all over the planet, which is important, but it's also the intensity and how much dust is physically present in the atmosphere that makes the difference between extreme dust events and local or regional events. I'm going to focus specifically on regional and global scale events because the type of observations I mainly use are more sensitive to this kind of events. The local storms and dust devils, you need high resolution cameras to look at this kind of things. So this slide is a bit busy, but it gives you an overview basically of the projects I'm currently involved with. Some of which are ongoing, some have just finished, some are still, I'm still just at the beginning, and one in particular hasn't started yet, or at least let's say there are studies, but we haven't got to the point of sending a constellation of satellites to Mars yet, which is this project here. So the first one, let's say, is the project that maybe most of you know when you think about me, which is reconstructing dust maps from multi-satellite observations. And this is a project that is ongoing because there are always new observations coming, and so we can produce more and more daily maps of dust opacities. This is a project with the LMD, sponsored by ESA and CNES, but also by NASA, because I had a grant when I was in the US to improve this data set. Give you some details about this project. This one, monitoring dust storms with an aerostationary satellite, is the evolution of what we're having now. So we have many polar orbiters, one satellite, the EMM mission, which has an interesting orbit, which is inclined by only 20 degrees. But the next stage would be to have a constellation of multiple satellites to really provide this complete coverage that we require to monitor properly the dust storms. And then the other two projects are related. So I have a project with master students to study, basically to take the product that we create, so the daily dust maps, and to study the statistics of the dust storms that we see in this product, because at the end you want to do some science out of just creating a product. And then this project here is take all these observations, put into a global circulation model, and produce a what is called analysis. So it's a data simulated product which combines observations and modeling, and you can use real observations. So you can only simulate synthetic observations to see what would be the impact of observations that are not there yet in terms of reconstructing the meteorology of dust storms or any other weather phenomena on Mars. So, because of time, I'm going to focus on these two topics. If there will be time left, and if there is interest, then we can briefly look at the others as well. So, what kind of instruments and satellites do I use to monitor the dust right now? Mainly American instruments, so Mars Global Surveyor TESS, Odyssey, Themis, and Mars Reconnaissance Orbiter MCS, Mars Climate Sounder. We heard about at least this instrument already. For current use, I started using also the EMIRS instrument, which is an infrared instrument on board the Emirates Mars mission. And of course, for future use, it would be interesting and useful to also add European spacecraft and European instruments. PFS has produced a long-term observations of dust, together with temperature and water ice, etc. And of course, we are here at the roadmap workshop, so NOMAD and also ACS on board TGO could provide additional observations to include into this high-level product. So the quantity I'm mostly interested in is the column dust optical depth. Okay, as you see, all of these so far are infrared observations. So I'm mainly using infrared observations, mostly from sun-synchronous satellites, whereas these ones would be non-sun-synchronous satellites for the first time. So optical depth, you probably know very well what it is. It's basically the exponent of this equation where T is the transmittance, so the ratio between the transmitted radiant flux divided by the received radiant flux, and tau is basically the attenuation through the atmosphere. And when the radiation is emitted from the surface, this is infrared radiation, then it goes through the atmosphere, it is absorbed and scattered, as we learned very well in these 3 days. And then the Nadir viewing instrument look at what is left, and then we can, people doing retrieval can derive this tau, which give us an idea of how opaque the atmosphere is. Okay, right. This is an example of what we can create by integrating the single observations. So this is an example using Mars Global Surveyor TESS in Martian year 24. It's a long time ago now. We are in Martian year 37. So I produced this animation a long time ago, but it's still valid, I would say. So TESS, of course, is a polar orbit. Yeah, it's a sun-synchronous polar orbiter. So it observes in stripes, and the stripes move. Okay, so it's quite hard to distinguish what's going on here. So we use a technique which is called iterative weighted gridding and then we do some interpolation as well with using kriging to produce a complete latitude longitude map of the column dust optical depth. So if there is a storm, now we are able to see it pretty clearly. We see the evolution. We can calculate some statistics, average opacity, centroid, trajectory, and so on and so forth. So it's a higher level product that is based on real observations. So there is a bit of magic in this process. The magic is described in these two papers. If you need more information, we can click on this information point. Otherwise, let's move on, and we can come back to more details if you want more details about the methodology. So when we produce these daily maps, then we can average them together to create the long-term climatology and look at the interannual variability of these dust opacity values. We can plot them in solar longitude on the x-axis and latitude on the y-axis, and we have this kind of zone and mean plots that people showed several times, which are actually quite nice because you have an idea about first repetibility of these events, but also variation from year to year. Okay, so you clearly see that there are years where the dust peak is very high. So red is very high values, pink is very low values of opacity, and these are the global dust storm or extreme dust events, however you want to call them. We had one in Martian 25, one in Martian 28, and one in Martian 34. Then we also see that there are other peaks which correspond to less intense events. We can call them regional storms, and they almost appear at the same season or same solar longitude. And the first part of the year in terms of dust is quite boring. We know that we have just a background dust, but no specific dust events, at least not large-scale dust events. There are always local storms, but not large-scale events that increase the atmospheric opacity by that much. Now, if you take the average of this long-term climatology, then you have one single plot, of course, which tells you more or less when and where you expect the opacity to increase in the Martian year. So you have a first early peak, which usually happens between 1 LS solar longitude 140 180. Then we have a main peak, which is later, 220, 240 LS. You have a southern high latitude peak, which correspond to the retreat of the southern polar cap, and finally a late peak around solar longitude 320, 340, with a hiatus in the middle, a gap in the middle. Okay, do we understand these peaks? We do at certain degrees, at least this kind of peaks. I should tell you that the previous, this plot is created without the global dust storm data in it, because otherwise, of course, you would see a very large peak emerging. So these are basically only regional storms, large-scale regional storms events. Now, how do we understand this peak behavior? Well, we understand if we link this plot with what we know about the dynamics of dust storms and weather patterns on Mars. Without many details, this diagram here is showing the molar topography, but overlapping there is a surface pressure anomaly, which basically shows you, let's say, the typical waves that you expect at these higher latitudes during the Martian autumn and winter. These waves are kind of equivalent to the waves that we see in mid-latitudes on Earth, right? And they produce weather patterns. In particular, here I'm showing surface pressure anomaly. So you have a low pressure, high pressure anomalies. These are linked to wind gradients. And of course, when you have a wind gradients, you have wind stress, you have the engine that can lift dust from the surface. and move it around the planet. Because not only you have waves in the northern plains, but you also have currents that follows the boundaries of the topography. Particularly, you have the three typical boundary currents. One starting from the Acidalia area and going south, and one from Utopia, and one from Arcadia. So these are called sometimes storm tracks. We have storm tracks on Earth as well. So let's say they are preferential directions where dust tend to move, and while it moves, then the dust storm becomes larger and more intense. And in fact, we can link this peak of opacity to exactly the timing of the appearance of these waves. Now, of course, you have to do a data simulation to link a specific dust event to a specific wave that occurs at a specific time. But in general, either the main peak or the late peak in opacity are linked to these waves that occurs in the northern hemisphere. Now, there is a gap between these two peaks. So what is it? What happens at solar longitude 270? Well, what happens, we call it a solstitial pause, and it's a dynamical phenomenon described in a couple of papers at least, if not more, where we understand that something going on in the northern hemisphere, particularly the cold temperature make water ice and CO2 ice condense, and this has dynamical effects on winds that basically shut down the intensity of these waves for a while. And because these waves are no longer very active, then you have no longer enough wind to lift the dust, and therefore you have no longer storms occurring in this period of time, and we clearly see it in the peaks of opacity. Okay. Now, this product is publicly available. It's publicly funded for the time being, at least. So we make it publicly available. It's publicly available in the Mars Climate Database project webpage. So if you go to this link, then you will need to look for Martian dust climatology. And in particular, when you look for Martian dust climatology, look for climatology of Martian atmospheric dust. You click there, and you will end up with, basically, if you click on this link, the same thing. So you will end up on the page where you can download this data set in NetCDF format, so easy to use, I believe. And then you can do your studies or use it for your models or whatever. So there are two kind of products. One is just observations, and one is observations plus some interpolation, and that's mainly used by modelers because they need a full longitude and latitude map, which has no gaps. Okay, so that was so this data set has from Martian year 24 to Martian year 36. Now, I had another project specifically with NASA, and we were retrieving dust optical depth as well as water ice optical depth in the infrared, but also in the visible using EPF for the TESS instrument. So we were kind of going back in time, taking TESS observations and retrieving the opacities, because we realized that we did things in the early days which could be improved. So we improved those things. So we I didn't, but Mike Smith and Mike Wolf retrieved these opacities for infrared and visible. So now these 3 Martian year of tests, actually almost 4, but partly Martian year of 24, the full Martian 25, full Martian 26, and partly Martian 27 are available on the PDS, NASA PDS. Again, you click on this link, and you end up with downloading these new retrieval data sets. At the same time, I produce also new maps, new daily maps, so the high-level product. So you can also download the high-level maps coming from these new retrievals. Fortunately, the PDS does not support netcdf file, so you will have to read ASCII files. It's a bit boring, I guess. netcdf will be much more practical to use, but I think in due term, maybe this same maps will be available on the MCD webpage with netcdf format. Okay, so that just to show you that this work is not only about climatology, it's about meteorology. Okay, so we are really looking at the evolution of dust opacities day by day and even sub-daily with the Emirates Mars mission now. So I'm showing you an animation that has one sol per frame for 3 Martian years. So we have Martian year 24 here. You don't see it because there are no data yet. Martian year 25, 26, and 27, which disappeared because there are no data yet. No data anymore, sorry. So you see the evolution of the dust opacity. Now it's boring because we are in the first part of the year. You know, we are in LS 114. So there is always a bit of dust opacity because of local storms, particularly in the northern, around the cap edges, but nothing in the middle. Then we'll come to the more interesting time, and you will see the appearance of dust storms. You can follow the evolution of them. So it lasts for a couple of minutes. So maybe I stop here. If you have any question, ask me now while you observe the movie. The movie gives you the time to think if you have any question. Maybe you can ask later. Now you see the storms, right? Now you see what's happening. And this is the big extreme events of Martian 25. So you see that it's an order of magnitude larger than any other regional storms. And then we go to the gap between the main peak and the late peak. And then you will see that when the late peak that I showed you before occurs around 320, there will be storms. Here we are, Martian 26 coming. There will be another storm, Martian 25, slightly smaller. And there might be another one in Martian 24 as well. By the way, what I called early peak, main peak, late peak, other people call them storm A, storm B, no, storm A, B, C, something like that. Right. I prefer not to use this terminology because it's not a single storm. Every storm is different. It's more about the seasonality. You know, you have a seasonal peak, and but this is just question of nomenclature. So, right. EMM. With EMM, we have access to a novel way of looking at the planet because EMM has an orbit which is inclined by 20 degrees. So we observe the equator with a large field of view. All right. The field of view moves, but we are able to really to see a big chunk of the planet at the same time, simultaneously. So it's the first real, let's say, well, it's a kind of the first view of a continuous, simultaneous, but not global coverage of planet Mars. And it's a mission dedicated to the atmosphere, so we really get the most of it. So because of its orbit, we are able to feel the gaps much more than with polar orbiters, and we also explore different local times. So this is an example of a regional storm that occurred in Martian 36, reconstructed using the EMM results, EMM retrievals, always in the infrared. So I'm still using one map per day or per soul. This occurred in 2022. But the advantage with EMM, which we couldn't have before, is that now we also have the possibility of looking through multiple local times. So now, instead of just one map per day, I'm showing you 4 maps per day or per soul. So the local time at 0-degree longitude changes. Okay, here is midnight, 6 o'clock, midday, and 6 p.m. Okay, 6 a.m., 6 p.m. So what is interesting is that when you look at the evolution through the local times, you see things that you couldn't see before. This one is, I believe, a first example of, I mean, a very clear example of lifting of dust occurring, between, at least between the morning and the evening. So we see that the opacity is increasing between these 2 frames. So there are results that I couldn't show you yet because EMM has a particular procedure to show results. But we made some comparison with visible images, and I can tell you that you are really seeing something changing from one frame to the other one. So I believe this is we captured a dust lifting event. So the potentiality for EMM are large. Now the potentiality for EMM are large, but then what's next, right? What can we do better, even better than EMM? How can we do monitoring even better than we are doing now? So this is a warning. Next big things ahead. It means now I'm entering into workshop mode, right? So this is just for discussion purposes. There's nothing written in stones anymore, any longer. Before it was a bit clear. Now it's more like rambling around the concepts. Okay. Give you the warning. So let's move on. What we need, of course, as I told you at the very beginning, we need continuous observations. I mean, we kind of already have continuous observations. We have been continuing observing Mars at least from Martian 24 onward. Global observations, okay, we kind of observe Mars globally because we have a global coverage. Our spacecraft move in space. The thing that we don't have yet, and it's crucial, is a simultaneous observation. So we don't have these 3 things at the same time. So we are not looking at the same location all the time over the whole planet. And that would make a big difference because we could, instead of reconstructing these dust storms using these magic statistical functions, we could really observe what's going on in real time. To give you an idea of what I mean is I'm creating here some synthetic wish, let's say, of what it would be nice to have. So it would be nice to have at least 3 views of the planet simultaneously, which would give you at least between, let's say, 60 north and 60 south, a full observations. And then it would be nice to have, this could be achieved by a nadir-looking instrument. And then it would be nice to have a limb scanning instrument on a polar orbiter, for example, that can provide us with the vertical distribution of the dust. So if you had a combination of vertical distribution of the dust plus the horizontal distribution of the dust, I guess you will be really looking for a very accurate monitoring of dust events and other weather phenomena, of course. So by the way, this is an assimilation product. So we used MCS vertical profiles to inject these profiles into a GCM, and then we have this 4D product. By the way, open brackets, is a simulation product using MCS and tests will be publicly available soon as well. This is one of my projects, so I have to put online, so stay tuned. Right. Unfortunately, these 3 views, they are not there yet. At least we had MCS to help us to produce vertical profiles, but we don't have a 3 spacecraft right now orbiting to give us these beautiful views of, for example, a global scale event. Okay. So we need a constellation, right? Which means we need a multiple spacecraft on orbit at the same time. And we work on that because we as like some colleagues in the United States and some colleagues here in Europe, we went to JPL. We sat there for like 3 times for a few days, and we came out with a mission concept, which is I call it the ultimate Mars satellite constellation, because it has 10 spacecraft in the constellation, right? So everything you want to know about the atmosphere of Mars, plus the surface and a bit of subsurface, this mission is able to give you. It's called Mosaic, because it helps you to create a mosaic of different phenomena on Mars to make the ultimate picture of the climate system on Mars, right? So it's a very climate system focused mission. So great, but we submitted to the decadal survey, and the result was, yeah, that's great. It's a very large class mission. We have Mars sample return campaign on our way. Of course, this is too expensive. We cannot fund it. But the interesting part is actually this. Some of, I mean, a portion of the science may be achievable within lower cost implementation choices. So the key here is, the keyword is low cost. What 2 words? Low cost. Getting something to Mars at a lower cost could pay. And that's where we gathered together many people, again, internationally, to agree on what we would need for what would be the best approach for providing us with this continuous, simultaneous, and global Mars weather monitoring. So I managed to at least convince around 52 people, spanning from the United States to Europe, to the Emirates, and to Japan, to write a sort of community paper that we submitted first to MAMO, and then we presented to MAMO, COSPAR, EPSC in Granada, of course. I mean, I hope that there will be even more people that agree on this approach. But that was the number of people I could myself contact, you know. So then if there is other people interested, you are absolutely welcome to join us in this approach. And the key point of the approach, I would say, is to consider the modularity of sending spacecraft and instrument to Mars. So instead of like one big mission doing everything, let's try to do many smaller missions doing parts of the whole story. Basically, instead of doing a one mosaic mission, we send many missions that create a mosaic, right? In a sense. So what is the bare minimum? Okay, so the bare minimum, well, the bare minimum is one spacecraft, okay? We all agree on that. But the bare minimum to do something more advanced than we have been doing so far, we believe, is at least one polar orbiter and 3 aerostationary orbiters. So these aerostationary orbiters are the equivalent of geostationary satellite for Earth. They are located at very high altitude, 17,000 kilometers. So an instrument has to have it cannot have like a very small footprint, you know. unless you really have an instrument with a very high resolution. But the good thing is that they could have a full disk view, which provides you with a full coverage of many locations at the same time. And then the bare minimum in terms of payload is to have a visible camera on all of these. We believe a thermal infraradiometer looking at nadir and limb will give us at least, the retrievals of temperature, dust, water, ice in the vertical and in the horizontal. So you have access to all these quantities. With this package, you get a three-dimensional global continuous simultaneous observations. Great. Then, of course, you have more budget. You can add your wishes. So if you add 2 or 3 small polar orbiters, it could be CubeSat, then you have vertical profiles at several local times at once, which is a great advantage. You add another aerostationary orbiter. You add the stereo capability, which provides you with, for example, you can get the altitude of the clouds. You can track the cloud to get some information about the wind. Then, of course, you have more spatial coverage because you have some overlapping. And if one breaks, you have still 3 to play with. You want to add more? Then why not? You have possibilities for near-infrared spectrometers, can also provide information about surface pressure. A UV camera, of course, which together with a visible and a thermal infrared would allow for multi-wavelength aerosol retrievals. And then if you really want to be grand, you put a sub-millimeter sounder and LiDAR on the polar orbiters. You have access to wind profiles, plus space weather package on the aerostationary, even look at space weather. So you see that when we get here, we get mosaic, right? But then we can start from the very beginning. So I would be already very happy if we send one aerostationary orbiter, which would be different from whatever we have done so far. Okay. We thought about it, all right? We thought about taking mosaic and just retaining the minimum that we consider is useful to send to do something much better than has been done before. And we call this concept macaws. Macaws are these beautiful birds, very colored birds, okay? So MACO stands for Monitoring Aerostationary Constellation. So it's an aerostationary constellation of 3 spacecraft for atmosphere and weather in space. So you can look down in nadir and produce the usual, map of aerosols and temperature. But you can also look back to space and have information about incoming radiation, so that you have you do space weather monitoring. And you can do that because the altitude of this aerostationary spacecraft is 70,000 kilometers, which is well above the bow shock. The bow shock is the limit between the magnetic field of Mars and the rest of space. So because you are at least 75% of the time outside this bow shock, you have access to direct incoming radiation. So you can do space weather monitoring. Okay. So this concept was originally submitted to ESA. There was a call called What's Next? New Space Mission Ideas and Concept. It was in COVID time. We had a lot of time. So we came out with this idea and we submitted. And it was kind of, well, it went up to the point where they were considering it. And in fact, ESA has a concept called Fahrenheit, which has an aerostationary component in it. But the good thing about this is that, okay, they didn't yet decide to fly this concept, but at least we got a project with them to study quantitatively what would be the impact of having these 3 spacecraft and other possible configurations on the monitoring of the Martian dust storms and weather in general. So at least we have now not only a concept, but we also have some quantitative numbers to give to space agencies to say, well, if we only have a polar orbiter, you get that. If we add more platforms to these constellations, then we increase by 20%, 30%, 35%, depending on what you want to look at. Okay, again, if you want more information, more specific technical information about my course, we can click on this information tag and we'll have access to more information. If not, we can always come back. If not, I still have a big thing ahead to mention to you about. So let's suppose in the future, maybe not far future, but at least in the future, that we have more observations coming. You know, we have these constellations in place. We have you know, multiple information coming from different spacecraft, and we had to integrate all this product into, you know, a high level product that is useful for the community. What I think we need at that point would be a CM3F. What is a CM3F? Okay, let me show you. Center for Mars Meteorology Monitoring. And then I put in bracket forecasting, because forecasting is still tricky. You know, it's not that having more orbital information we can do forecasting better. You know, really had to also have to go to the surface and get information there to improve the models. You know, we know that very well in roadmap, right? You were exactly doing that. You know, you really went from the ground to the atmosphere to improve the GCM. But at least the CM3 part can be done, and can be done, to be honest, it can be done even today. It can be started from now onwards, because we have multiple satellites coming in, multiple observations, so we would need a coordination. We kind of, we are doing it already. You know, I'm doing it. I'm taking all of your beautiful data, and I'm trying to integrate this data into a product that the community is using, and really the feedback is good. People want these kind of products. Now the question is, there is a limit to where I can do it. I think it's much better to have helps, or at least to cooperate, to partner with people that can bring this project much further. So the question is, who are the possible partners that could join me into this effort to create this Center for Mars Meteorology Monitoring and Forecasting for the future? So I told you at the beginning, me as Pan-Eureka, I am an enterprise. So it's quite well seen now in Europe and elsewhere to have a partnership, you know, private-public partnership. So maybe this question mark should be some public institutions that, you know, joining forces, we could really not build a building. Maybe the building is already there, so we can just we need to. I mean, it could be virtual. You know, it doesn't need to be a building, but somehow it has to be identified as a specific and independent organization or enterprise. Okay, so my time is nearly over. We went to the Belgian Beer World yesterday. I like this quote because I told you many things that I believe, of course. So everybody needs to believe in something, you know, and this American actor Fields was saying, yeah, okay, I believe I will have another beer. So after all these, you know, great things, just let's have another beer, and not any beer, okay? Let's have a Martian Das beer, okay? Should put a copyright, because I created this yesterday at the beer museum. Okay, I have done. So any questions, please feel free. If you absolutely want to know more about the other projects, then I have backup slides for those. Thank you.
So you mentioned this test data set want to call it? Do you want to maybe mention what's new in there? I'm sure you compare to the old one.
So the main, well, first of all, there was a small mistake in the previous retrievals that has been corrected. So that's quite important. There was a code mistake. Sometimes happens, and then you leave it for many years, and everybody's using your retrievals, and then there was a bug in my code. So we corrected that. But to be honest, we didn't write a proposal to correct the mistake. So the main point was, with the advancement of retrievals in the infrared, also take into account what we are learning from EMM, we can now push the retrievals into areas where the surface temperature is colder than before. Okay, so before, when the surface temperature was below a certain threshold, the retrieval was just not provided because that certainly was too big. So now Mike Smith has being able to push the retrievals much farther when it's cold. So we have an extension in the edges of the polar cap, and we see a few more things that we were not able to see in the previous data set. Plus, we also re-retrieve the water ice. So now people like Antoine can finally use this this water ice data set publicly available. Plus, this is totally new. We also retrieved the visible opacities using the EPF, so emission phase function observations that were not done before. This is Mike Wolf's work. So we now have kind of simultaneous data set, infrared, visible, that we can compare. And I hope it's going to be interesting and nice.
Yes, so workshop-wise, one comment would be that if I would be agency, I would fund macOS because that looked pretty colorful and cool. CM3F, I'm not sure.
Not colorful enough?
Huh?
It is not colorful enough, maybe. Yet.
The building was okay, but the name is...
the trees. I know the trees are the problem.
Sometimes it's only the name makes a difference, I guess.
Yes.
Anyway, my question would be, well, you showed this climatologies, suggesting that you have these storm tracks going downwards. And if you have some dust in your atmosphere, you always have to have a source on the ground. So does that suggest you have some net source at the polar caps and it's all kind of concentrating or raining out also in this lower latitudes there where you have all this activity? Is this not a specific question, just is it something going in this direction?
It's okay. So could you click on this one, the blue information? So of course, we don't only create products, we also try to do some science. So when we take these maps, then we use different methods to extract the key information, like in this case, high dust opacity values, which means dust storms. And then we identify events and we can study the statistics of them, okay? So far, a student has been doing it by eye. Of course, there are methods using machine learning to do it automatically, but that's not the problem. The nice thing is that he has identified already 71 large-scale events, and we could do some statistics. So Clearly, the first thing that you see, this is not extremely new because it has been already seen in images, like visible images. But clearly you see that the origins of these dust storms are mainly in the northern plains, where indeed you expect to have not only the right dynamical conditions, as I showed you before, these waves, but also you need to have a loose material to lift. Otherwise, where is dust coming from? Okay. So mainly they come from these three regions with different ratios. The acidalia is the one that provides more events, but then Arcadia Utopia also follows up. This is another view which shows you on a map where the origin of this storm is, and indeed it's mainly in these northern plains, at least for these large scale events. I'm talking about. Plus some around Hellas. But then the interesting plot I think is this one, which shows the trajectories. So what happens is that the origin is in these areas, but then these storms tend to follow a topographic boundary, okay, and being entrained in this corridor, or these corridors, because there are three at least. And then when they cross the equator, they are already at high enough altitude to be caught by the global circulation. So I believe that this part is mainly happening close to the surface. And then when you get to the equatorial region, you are much higher up, and then you get spread. And in fact, basically you cannot follow the trajectory anymore because dust is no more concentrated, is diluted, becomes like a cloud rather than a very identifiable dust storm. Plus, you have the odds events around the Hellas Basin, but that's also because the wind is particular there, and possibly you have some availability of dust that is around the area. Does it answer at least partly your question?
Luca, this is Frank online. These tracks, are they from observations or models?
No, these are from observations. So what we do, we take the maps and we identify just the storm. And then once we have identified the storm, we calculate the statistics just within the boundary of the storms. So we are able to track the centroid of the storm and the intensity or opacity, the average opacity of the storm. So we have access to information like, centroid position and area and intensity. And then we can plot all this information as we wish and do some statistical analysis. Sure. Thank you so much.